Hey chemistry students, this is Mrs. Miller, and today we're going to go through our second set of notes, which is going to be on radioactivity. It's easy as A, B, G. Get it? That's kind of funny. So A is going to stand for alpha, B is for beta, and G is for gamma. You can also see their little Greek symbols here, and we'll be talking about those in a little bit. You guys should all have a red reference sheet that probably says nuclear decay information treasure hunt or something along those lines, but it's going to have these 4 questions starting with what is radioactivity, ending with the decay of an unstable isotope, and then you're going to see this type of decay chart. So what we're going to do today is with these notes, you're going to be able to fill out every single piece of this. This reference sheet can be used on tests, it can be used on quizzes, so it's to your advantage to complete this properly. So if you have any questions about this sheet, make sure you ask your teacher. Our very first question that you guys are going to respond to is, what is radioactivity? So that should be the first question in your red reference sheet. The answer to that is radioactivity is the process by which an unstable nucleus emits one or more particles of energy in the form of electromagnetic radiation to become more stable. So I'm going to fix this instead of or. I'm going to write of. So it makes a little bit more sense. So what we have is a nucleus usually is going to be unstable either because of the number of protons to neutrons in the nucleus or because the nucleus is really, really large. So the larger the nucleus, the more unstable it tends to be. And every nucleus wants to be stable, so it's going to decay until it is able to be stable. So one of the most famous sites that has a lot of radioactivity is Chernobyl. Some of you guys may have watched, I believe it was an HBO series. It's phenomenal, but it really does go in depth on what happened with that particular nuclear reactor and how that location is still extremely radioactive now, some of the health issues, and it also talks about some of the different animals that are still living there or are living there again, and some of the effects that are on them. What we're going to do here is we're going to talk about our 3 different types of particles, and we're going to go from the slowest to the fastest. So our slowest particle is going to be the alpha particles. As you can see here, they're also going to be the largest of the 3. So we have alpha, beta, and gamma. I'll write that down for you guys so you can see that. So alpha, beta, stop doing that, and gamma. Okay, so what we're going to see with alpha decay is we have an alpha particle, and because alpha particles are relatively large, they can't get going as quickly. So what we're going to see is alpha particles are going to be stopped by our skin, so that's good, or a single sheet of paper. So alpha particles are going to be going all the time around you, but they're not really going to impact you because they're very, very slow. Our second type of radiation is going to be our beta particles. So beta is going to be this bee that has a tail on it. And what we're going to see when you compare the alpha particle down to the beta particle is it's smaller. Because it's smaller, it tends to move faster. So because of that, it goes right through the sheet of paper. However, the beta particles are now going to be stopped by the aluminum foil. So here we have our aluminum foil, here we have our paper or skin. So alpha particles stopped first because they're largest. Beta particles are going to be moving faster, so they go through the paper or the skin, but they are going to be stopped by aluminum foil. Then last but not least is going to be our gamma rays. So gamma rays, notice that we don't see a particular particle. Instead, we're going to see that it moves as a wave instead. As you can see, this wave goes right through the paper, right through the aluminum, and most of it is going to be stopped by lead. So what we can stop gamma radiation with is several centimeters of lead or 12 inches of concrete. That is why around nuclear reactors, oftentimes you're going to see at least 2 feet of concrete around that reactor to try and prevent any of that nuclear radiation from coming out. So what you can see here is our little symbol for gamma. So it looks kind of like a fancy Y. So it looks kind of like that. What you're going to see is with that lead. Think about it for a second. Have you ever gone in somewhere and had lead put on you? You probably have if you've been to a dentist, if you've ever gotten an x-ray. So what they're using is a lead sheet that they're putting over your body. Notice it feels really, really heavy. And that is to prevent any of that gamma radiation from getting into you. So they only want to put radiation in the part where they need to see that specific bone or those specific teeth, whatever it may be. And notice that they don't do x-rays very often, and that's to prevent any sort of radiation poisoning to humans. The next question that we have on your reference sheet is, what is the relationship between an alpha particle and a helium nucleus? Well, they're the same. An alpha particle is a helium nucleus. So here we have our alpha particle. So remember, that's like that weird A. And what you can see is we have 2 of our red protons. We also have 2 of our blue neutrons. And it's going to have a little charge on it because there's no electrons with this. So this is just like the nucleus of helium. So what you can see here is we have our symbol. Remember from our last video, we have our atomic number on the bottom, and then we have our mass number on top. So because when we look at this, there are 4 particles. Each one of those have mass. That's why we have 4 there. We have 2 protons, which protons are our atomic number. So those 2 are going to be the same thing. As we continue down your red reference sheet, the next question is the decay of an unstable isotope into a stable isotope always a one-step process? So first and foremost, I want to remind you guys what an isotope is. Remember, this is a nucleus that has a different number of neutrons than normal. So it might have extras, it might have lost some, but what we're seeing is we always want to go from being unstable to being stable. So is that always a one-step process? Heck no. Oftentimes what we're going to see is the nucleus is going to decay into another nucleus that is also unstable, which leads to a decay series. And I'm going to show you what a decay series looks like in just a moment. So here's a great example of a decay series. So we're going to start out with our very unstable nucleus, and in this case that's going to be uranium 238. It's going to go through alpha decay to become this, then beta, beta, alpha, alpha. Notice every time it's either a new element it is a new element, and we're going to also have a difference in mass. So as we keep going down, it keeps decaying until we get all the way down here, which we finally get something that is stable. So we have lots of different intermediates. Some unstable nuclei are just going to go through a one-step process. So for example, if I had polonium 210 right here, it would just go through one step and then it would end up being lead 206. So that's just a one step. However, you can see that there's a lot more steps as we go through with uranium. Now what we're going to do is we're going to start to fill out some information with the data table on the bottom. So we need to first remember what an alpha particle is. Remember, an alpha particle is just the nucleus of a helium atom. So we're going to have a few different ways that we can draw this. We can do the little A, which means alpha, that has the atomic number of 2, the mass of 4, and then the charge of +2 because there are no electrons. We could also see it as 2, 4, +2 with an HE because those two symbols are interchangeable. Alpha and helium mean the same. Or we could just simply go with the A, the alpha particle. It's a lot less descriptive though, so we're going to prefer those first two. And here we have our alpha particle with 2 positive protons, 2 neutral neutrons. All right, guys, so now we are on our first line that we're going to be filling out. So as you can see, we have our alpha decay. where it says NZ is too large. So what is N? That means the neutrons. Z means protons. So essentially it's saying that the number of atoms or particles, inside of the nucleus is too large, so it's going to have to decay to become stable. So what is going to happen, literally what you guys are going to record in here, the change in atomic number, is we are going to see a decrease of atomic number by 2, meaning 2 protons are going to be given away. At the same time, our mass number is going to decrease by 4, and that makes sense because we are getting rid of an alpha particle, which has 2 protons, 2 neutrons, so 2 plus 2 is 4, right? So the particles or rays that are going to be emitted is going to be either an alpha particle, or we can draw it as a helium, which I prefer. So the 4-2He, then you can keep track that your mass went down by 4 and that your atomic number went down by 2. So if we were to draw out a very generic type of reaction, we would start with our first atom. So in this case, I'm just using X because obviously we know nothing X is on the periodic table, with Ba. B is representing our atomic number, A is representing our mass. Then what we're going to see is we're going to create 2 new elements here. So we're going to create new element Y, which has 2 less protons and 4 less for the mass. Plus, we're also going to see 4-2He with our plus 2. So this is our alpha particle. Okay, and that makes sense. So every time we see alpha decay, we have to see an alpha particle. So here's a great sample reaction. Didn't fit perfectly, but we have 238, 92, and we have U. So we're starting with uranium. Uranium, as it starts to decay, we know that we need to decrease our atomic number by 2. So 92 minus 2 is 90. And then we're going to take our mass and we're going to subtract it by 4, like we see here. So we see 238 minus 4 is going to be 234. So to figure out what that is on the periodic table, look up number 90 and you're going to see TH as in thorium. So now we've done that, and now we just need to add in our alpha particle. So 2,4He plus 2, okay? So every time we drop our protons by 2, our mass by 4, that's how we're going to do that, and then always add in our alpha particle. So whatever we have on one side, it has to equal the other side. So if I take 234 plus 4, that equals 238, right? If I take 90 plus 2, that equals 92. So you have to make sure that they are equaling out on both sides, and that's the way that you tell if you're correct. The next one that we're going to move on to is our beta particles. Remember, this is like an electron that's moving really, really fast. So the symbol that we're going to use for this, we have 3 of them that we could use. We have this B that has a tail toward the bottom, the B that has a tail toward the bottom and has a -1 charge. Notice it's an electron that is moving. So it makes sense that we have a charge there, right? Or the other thing that we can do here is we say -1, 0, E to show that we have an electron. So what a beta particle is going to be is that little electron that's coming off. So before I get into this, remember, this is a reference sheet for you guys. You guys do not have to memorize this at all. So our type of decay now is our beta decay. Again, why we have beta decay is because the NZ is too large, or the neutrons to protons, again, are too large. And what we're going to see, the important pieces here are going to be our first 3 boxes. Our change in atomic number, this time we are going to be increasing our atomic number by 1 because we're taking 1 away with that little electron. There's going to be no change in our mass number. And then we're either going to give up a beta particle or what we see with a beta particle here with that -1, okay? So if we had a really, really generic thing here, we have N that has a 1 and a 0. What we're going to do is we're going to change our atomic number by 1. So we're going to add 1. Mass stays the same. So now we have our new atom, plus we are going to have our beta particle. So again, this is going to be our beta particle. So if you ever see this particle with the -1 on the bottom, the 0 on top, and an E, that's a beta particle. That means you have beta decay. So a great sample of this would be, we have carbon 14. So carbon has an atomic number of 6, mass of 14. What we're going to do, we're going to go back here. First, we're going to change our atomic number. We're going to increase it by 1. So 6 plus 1 is 7. The next thing I want to figure out is my mass. It says there's no change for mass, so I'm just going to drag that over. So 14. To figure out what this actual element is, again, we're going to be looking at our atomic number. So I look up 7 on the periodic table, and that is nitrogen. And then I also need to have my little beta particle shown here. So my -1, 0, E. So again, we saw an increase of my atomic number by 1, mass stayed the same, and we saw a beta particle. Last but not least, we have our gamma rays, and we're going to have 2 types of gamma radiation. Gamma radiation means that there is a high amount of energy, and we have a few symbols with that. So you could do the little weird Y like that. Some people also like to do that guy as well. Either one is fine with us, but it has a 0 and a 0 with it. And then as you can see down here, we have our gamma rays. Our gamma rays, as you can see, are much closer together than things like radio waves, so they move very, very quickly, and that's why they're so damaging. What we have here is we're going to discuss 2 modes of gamma radiation. Our first one is going to be electron capture. The reason why we have electron capture is because we actually have too many protons inside of the nucleus, so they're too close together, and because they're too close, it's a lot of repulsion forces. What we want to know is, again, the first 3 things that are going to show what's going to be occurring. So, change in atomic number, we're going to decrease our atomic number by 1. We are going to see a change in the mass number, which is going to be no change. And the particle or ray emitted is going to be that gamma ray. So here is an example of what we would see. And there's a few things I want you to notice, but I'm going to look at it on that sample reaction just because I like this better. So first we have Cr. Notice that we have our atomic number of 24, our mass of 51. So this is the first time we're going to see something on the left side. And do you recognize what that is? Well, that's a beta particle, right? So left side beta particle. That's right away going to be a dead giveaway that you have electron capture. Okay, so this is going to help us figure out what we put on the other side, right? So we have 24 minus 1. That's 23, right? That makes perfect sense. And we take 51 and 0. That's 51. That makes sense. We should have dropped our atomic number by 1, so we went from 24 to 23. And we should have had no change in our mass number, 51 to 51. We have to figure out what our new atom is going to be. So we have V now. And then we also are going to see our gamma ray. So those 2 things, the left side beta particle and the gamma ray on the right side, if you see those things every single time, you are going to have electron capture. The last thing that we're going to work with is something called positron emission. Again, this is resulting because there's too many protons in the nucleus. What you're going to see here is you're going to see much of the same information. We are going to see a drop in atomic number by 1. We are going to see no change in our mass number. But what we see here is a positron, or it forms 2 gamma rays. So what's a positron? Well, that's an important thing that you also might want to write in here. And that's where we have E with a 0, but this time it has a +1. And that makes sense why we called it a positron now, which is different than a beta particle. Remember, betas have negative. Positrons are going to have positive. So what we're going to do here is you guys can fill in your reaction, your sample reaction. I want to go through an actual example here. So we have 4924 Cr. I'm going to go first and look at my atomic number. It says it's going to drop by 1. So 24 minus 1 is 23. Next, my mass number says no change. So I'm going to go 49, 49. I look at my new atomic number, 23, and I see that that's V on the periodic table. The thing that we're going to emit then is what we call the positron, which is a +1, 0, and an E, right? So when we add these together, 23 plus 1 is equal to 24. 49 plus 0 is equal to 49. So again, this little guy is called a positron. And if you see it, if you see this plus sign, that's positron emission. For electron capture, you have the beta particle on the left side, and you also have a gamma ray. For the other two, we had beta decay. We see the beta particle on right side. And by right side, I mean right side of the equation. And remember, that's a 0, minus 1 E. And for alpha, we see alpha particle. Which is a 4, 2, He. So those are the dead giveaways. If you see helium, that's an alpha particle. If you see beta decay, it's because this beta particle is on the right side. For electron capture, if you see the beta particle on the left side and a gamma ray, that's electron capture. And for positron emission, we have that positron that has a positive E. So now you guys should have that whole sheet filled out. If you guys have any questions, let us know.